Okay, the bulk cavitation, that's what we started. When you hear about the bulk cavitation, I want you to think about really white, the cavitation area near the free surface. That's all. Near the free surface, keyword. It happened near the free surface. And if you go down to deeper, there will be no bulk cavitation. There is no cavitation because of the hydrostatic pressure. It can't form the cavitation. It cannot form the bubbly water. Cavitation is a bubbly water, okay? So it always happens at the near the free surfaces. So in the strict sense, okay, in the strict sense, bulk cavitation starts just below the free surface, just below the free surface on the line of charge here, right here. This point should not really touch the free surface, but in a sense, who cares whether it's a touch or not? Why? Because it's the gap between the free surface and the top of the bulk cavitation. This distance is very small, okay? So then it has a curvatures coming through. But this is my freehand drawing, but as you will see a few pages after, it's not going to be just like this. It's going to be almost flat, going really, really far. Okay? So bulk cavitation. In your note, you don't have such a yellow mark, things like that, but for the lecture purposes, I put the yellows in there. Bulk cavitation, keyword. Tensile reflected wave or rarefaction wave or tension wave or surface reflection wave. It's all same thing. Very important keyword. And the vapor pressure. Vapor pressure is about 0.3 psi. About. Physicist is talking about 0.3 psi. For engineer, I don't care. That's near zero. So in the cavitation zone, inside the bulk cavitation, right here, inside, I don't care it's a 0.3 psi, 0.1 psi. You assume in the computation purposes to get the boundaries and all that, you can reset is equal to 0, okay? That's what you can do. And I told you read all the little wording in the paragraph. Is really fun to read. And the geometry for computation purposes. This is the standoff distance from image charge to the target. This is, I said, R naught. This R naught is the same, the distance from here to here plus to here, right? Because this distance and that distance is the same. So R naught, and this is a standoff distance from the charge to target is R. R is of course smaller than R naught. This is surface is incident, this is surface reflections, things like that. So I did the Wednesday, but I'm just redoing a little bit. If you miss it here, then you will miss it forever. And this is absolute pressure. And to compute the bulk cavitation zone, you have to pick out a point near the free surface. Then you have to compute the pressure. Then pressure, make sure, has to be 0 or less than equal to 0. And this is hydrodynamic pressure plus, hydrostatic pressure, up from the free surface up to the point that you have interest to compute. So PA is atmospheric pressure. Then here, from here to here, this is the shock wave pressure from here to here, P max. Then exponential decay, right? Then this is the time Tc. Tc is the time that the rarefaction wave hit the target. So this is max pressure for tension wave. And you have to compute. Students usually, not everybody miss it, but they should compute the P1 incident shock wave pressure at the time the rarefaction wave hit the target. Some students miss this when they compute the total pressure to check whether total pressure is 0 or below 0 to declare the cavitation. So this P1, remember, is not from here to here, P max. P1 is the incident shock wave pressure at the time the rarefaction wave hit the target, right here at the cutoff. This cutoff is right here. R naught, this distance, minus R over C naught. This is the cutoff time. So this is, so if you add the pressure segment together, it's going to come down here, up and down here, then sudden pressure drop, bang. If you simply add the numbers, it could go down here, but physically water cannot sustain the tension, so you have to correct the curve, so coming down. If it's below 0 or 0, you have to stop here, coming back up, and slowly get back to the pressure for atmospheric pressure plus hydrostatic pressure. So coming down, come back up, like that, okay? So that portion is important. And this is just blow up around here. As I mentioned, Wednesday, it could down up to this point, down that point, down that point. So this is a cavitation, this is a vapor pressure, 0.3, and this is a cavitation pressure. Cavitation pressure is like a 3 or 4 negative psi. As I mentioned, after I explained the physics, then in the computation, who cares? We're gonna reset to 0 to declare whether point is cavitated or not, 304 psi. Okay, and the exercise problem shouldn't be any problem, so you don't have to submit, but solve it in your leisure time, okay? And upper cavitation boundary. Upper cavitation boundary, to detect upper cavitation boundary, it's very easy to compute the total pressure. So something like this. The other side will be, of course, is axisymmetric. So you pick out any point. So you have to pick a lot of points, but to do that, you can make a grid. You can make a grid. You can go this way, and just using the do loop, you can check out the lots of points. Then after you get that, then you can draw connect the point where PT is 0 or below 0. Total pressure, okay? You have to compute the upper cavitation boundary. So P1 is incident shock wave pressure at the point the rarefaction wave hit the target. This, not the Pmax. P2, what's the P2 could be? This is Pmax for rarefaction wave. And PA, atmospheric pressure. PT is hydrostatic pressure at the target point. So to do that, I have shown right here the upper cavitation boundary. First term is this term. Does it ring the bell? This is e to the, this is P max. This is exponential decay up to the point, distance over c. You see, R2 minus R1. R2 is a standoff distance from target to, just watch this, target to image charge, which is R2 from here to here, which is equal to from here to here plus from here to here. Got it? That's R2 minus R1. So that's really, if you look at R2 minus R1 over C, is cutoff time, TC. Okay? So I use two different parameter, R1, or I use a capital R, which is really same, okay, in the equation set. So R2, R1, or R, this is XY point. This is a charge depth here. So geometry is just like that. Then back to here. So P1, you know what's the P1? It's not the Pmax for the incident shock wave. So don't confuse here. It's right here. I pointed out a few times, right here. This is that point. Pressure, right here. Dynamic pressure, no, this is a static pressure. So P1 is this, not this. I usually give a problem in the final to check out whether you fully understood or not. P1, to compute the bulk cavitation, P1 is this. P2 is clear. P2, okay, which term is P2 here? You have a full term. Incident shock wave pressure at the time the rarefaction wave hit the target is the first term. What's the second term? Atmospheric pressure, right? What's gamma Y? Gamma Y is hydrostatic pressure. Gamma is the water weight density, and Y is depth, right? Depth to the target. What's this term? Juliet, what's this term? It's a negative, which is rarefaction wave of pressure, right? That's what this is. And after that, it's all geometry, little geometry problems. So if you look at this, this is a geometry x, y, y. This is target depth is a y. Okay. Because we are considering this point, whether this point is cavitated or not. That's what we are checking. So by looking at this, if this has to be equal to 0 or below 0, if it go down to below 0, you know, the water cannot sustain the tension, so you have to reset to equal to 0. So if it's not 0, if this is a positive, that point is not in the cavitation zone. So then you have to move the next point and checking out and all that. Okay. So that's what. But for the lower cavitation boundary, not easy to detect. For easy the detection purposes, the different criteria is what they are using it, but still the PT has to be equal to 0 in any point in the cavitation zone, okay? But for the easy detection purposes, the Dr. Aaron, A-R-O-N, Aaron, in 1947 or 1948, he is the person who computed the cavitation boundary for the first time after Second World War. So he tested out, he proposed this. So since then, to compute the lower cavitation boundary, this is what we are using it. So here you have to define first the breaking pressure. Breaking pressure, I put a yellow line here. Let's define the breaking pressure as the rarefaction wave pressure, which reduces the absolute pressure at the point to the cavitation pressure. Forget about the few negative psi, but just assume 0. I'm going to read again. Defining the breaking pressure. Breaking pressure as the rarefaction wave pressure. Rarefaction wave, which is a tension wave, which reduces to absolute pressure at the point to the cavitation pressure, which is near equal to 0. So the lower cavitation boundary can be easily calculated by equating the decay rate of the breaking pressure set equal to the decay rate of the absolute pressure. Decay rate is d over the dr. This is a basic scheme to compute the lower cavitation boundary. So this is a decay rate of the breaking pressure. This is a decay rate of the absolute pressure. But still, you may not feel quite comfortable. So in another file, in your handout, or just a book, in the book, right after this section, you have another section, which I gave complete derivation for the whole thing. But right now you may not need, so that's why I didn't bother to go through. Usually I don't go through. Then notes is complete. And simplifying further, you have that equation set here. Then you have to solve this equation set That's what in another note in your book has it. And lower cavitation boundary right here. Lower cavitation boundary right here. It uses slightly different coordinate, and this is this point or that point is a function of r. Okay, r is the target distance to the lower cavitation boundary. This is the point. Then coordinate is alpha, this angle, and r. Okay, and extended point here is alpha, and r is the distance again from image charge all the way down to the point. So considering the decay rate of breaking pressure and the decay rate of absolute pressure, decay rate right at the lower cavitation boundary has to be identical. That's the whole scheme. And this pressure at small r can be expressed like this. This is, I just put that in to make sure. This is equal to this. You divide by this. You can express PR as P capital R and this, okay? Just explaining the basics here. This is what upper cavitation boundary. Then if you go through the calculation, then this G function has to be equal to 0 right at the lower cavitation boundary. So here the PI and theta I, PI, this is the incident shock wave pressure right at the time when the rarefaction wave hit the target. You see R2 minus R1 over C. And theta over here is right here. This R, capital R, is same as small r1. So usually I assign this to compute the cavitation boundary. I don't want to assign at this time. I want to assign another problem set. So you may, all the equation is given here, so you know what to do about it. So we're going to just pass it through. This is one of my students' homework problem set. So this is pentolite, type of the explosive. This is 100 grams, and this is 25, charge depth is 25 feet below the free surface. This is 50 feet. This is 75 feet. And look at the spread of the bulk cavitation. And then this is the center line. You can think about the axisymmetric rotation about this vertical axis. So here is for 25 feet charge depths. This is about 500 feet long. So about 500 divided by 3.3 to change to meter is a pretty big, 120 meter. Spread big. It's only 25 feet below. And 50 feet below, this is 700 around 20 feet. And for 750 feet, this is something like 700, 800, 900. So 800, 850. 850, it was 500 feet. So same charge size, but as you change the charge depth, which means when explosion occurs a little bit deeper, then white stuff is spread much wider. That's what this is telling. So you will see for this is a 200 pound the pentolite. This is a pound, by the way. I'm sorry. 100. I thought it's 100 pound. This sign is a pound, not gram. This is same as a pound. So this is the U.S. gravitational system. But if you look at here, for 25 feet below, for 200 pound pentolite, so this is something like 100, 500, 550, so it's about 530 feet, and this is about 500. So when you double, the spread is not as sensitive, about the same. But charge depth is very sensitive to spread, but thickness is also, this thickness is also different depend on the charge size. But charge size is higher, and depth, thickness of the cavitation zone is of course higher. So you can compute that, and the cavitation zone occurs, then it will close it very fast. So then whenever close it, then pulse, secondary shock also occurs. So this is student's computation. And another thing I want to show is like actual testing. For actual testing, this is of course a free surface, and there is the charge size, which is HBX-1. HBX-1 about 1100 pound, and gauge here, gauge here, gauge here. And this is what pressure gauge, okay? And the pressure gauge there, here is, so this is pressure, this is time. So you expect, I want to just show you the trend. So P max is from here to here is a P max, and exponential decay then suddenly cut. This is due to what? Due to the rarefaction wave hit the target, just suddenly cut. So pressure cuts here, then drifting around. This is all noise. So in computation and experiment, when you compare, result should be very close, but not top of each other. Even yesterday, we talked about that. So here's the pressure, the cut, just to cut straight down and drift around. This is all noise here. Go back up to the nominal pressure. Okay. So I'm insisting, if you can get the experience for testing, you should really involve in testing. And this is what I'm going to do the homework. This is homework due Wednesday next week, because it shouldn't take more than an hour. So I'm going to give you short kind of the homework. You can do in an hour. For bulk cavitation calculation, it takes more than 1 hour. You have to write MATLAB code. You have to execute actual plot. So you can do that, but this is what the homework, 3.3-8. Wait a minute. Not 3.3-8. So this is what the homework is, this. This point is 3.3-15, and here is the do this. You should be able to do very easily, but if you don't follow, then a little bit hard, but eventually you should be able to do. So think about this is a channel, horizontal channel or tube. Think about that. And right in there are two different kind of the fluid media. One could be oil, the other one could be the water. Okay? So one medium, fluid, one type, fluid, two type. And this is an interface between two. You could say this is oil, this is water, vice versa. And it flows in that directions. And here the incident shock wave hit, like a plane wave hit here. Fluid 1. Then this pressure is P1 and U1, fluid particle velocity here. And this is known. P1, U1 are known. Then it hit, okay? It hit. Then right at the interface, what happened? Some will penetrate, transmit into the fluid media too, and right at the interface, some portion of the shock wave will reflect. So it's right here. Reflection, I use a prime, P1 prime, U1 prime. And rho 1 C1, this is what the impedance for the fluid medium 1. This is a fluid medium 2, and this is a P2 and U2 is transmitted. The wave pressure is P2, and the fluid particle velocity is U2. So this is known. This, you know the characteristics of the fluid. Otherwise, no reason to solve. And P1 prime, U1 prime, unknown. You have to solve for this one. You have to solve P2, U2. Is it clear? So I want you to solve that, and the problem is all described here. Like first write the velocity and pressure boundary condition right at the medium interface. Then it shows all this. I want you to solve it. Any problem, see me or Higyu. Higyu went through all this about 3 years ago. 2 years ago. And exercise problem number 2, you don't have to worry, but you have some time, then you can solve it, okay? And back down to here is just the extension of computation. What this is telling here is this. This point could be the CG of the surface ship. You assume surface ship is long, of course. And this point is the CG of the surface. And the surface ship or floating body is in neutral buoyancy, right? Then this draft is a D, small d, and this is the charge depth is capital D. This is D. This is image charge. Phi I, the angle. This angle is phi. Okay. So geometry is completely defined. This distance, image charge distance from here to here is Ri, which is same as this. This is R, standoff distance. Then now you are considering this point, P here, same point here. And due to the incident shock wave, this point will have the velocity u1. Think this as a fluid particle velocity. Then you can compute the u1, fluid particle velocity of this guy. Or you can say u1 is CG, velocity of the ship, due to the incident shock wave. This guy is toward in that direction, which is called the fluid particle velocity due to what? Tension wave. Right? So moving in that direction. So this is near the free surface, like a naval ship, like a Cheonan naval ship. Young, what's the depth usually for Cheonan naval ship?
About 3 meters.
About?
3 meters.
좀 못했는데. Draft. Depth of the submerged section. About 3 meters. Okay. DDG class ship in US is about 23 feet, which means divided by 3.3, 23 divided by 3, about 7.5 meter. A meter, you're right. This is meter, not the feet. Not the 3 feet. 3 meters, about 9 feet. That's good. So the draft. What I was going to talk. This angle, phi and phi is about the same. Why? Because we are talking about usually shallow depth. It's not 50 feet below the water. Draft is not such a big. Even aircraft carrier, I forgot exact figure of the draft. The draft is depth of the wet part of the hull. It is not like a 50 feet below the water. It's still shallower. If this is a shallower, this and that angle is about the same, which means this angle, that angle are very close to each other. What that means, and U2, U1 is about the same. So which means the resultant vector always shoot toward the center. This is what the time to understand that. Because you have a ship here, explosion occurs way out there. This surface ship still kicks at the time of explosion, kicks vertically, okay? Regardless of where the explosion occurs. Right here, it's easy to see. This will kick vertically. When this guy is 100 meters away, 100,000 pounds, still this guy kicks the vertically up due to the tension wave. In addition to the incident wave, is summation of the vector always vertical. Okay, I'm going to stop here. The remaining portion, you can just read through some example problems that I generate just to practice. That's all I did here, except this one. Okay. Okay. So nearly done. 1 more week to go. 2 lectures. Scaling, I'll spend an hour, and the Taylor flat plate theory for fluid structure interaction. Very elegant to understand really what the fluid structure is, interaction is. Then Friday, I want you to prepare about 12 minutes per team, then make a presentation. Okay, that's the end of Friday morning talk. So have a nice weekend, and it's snowing, so I'll see you Monday morning.